Time to start sequential logic. Okay, so what is sequential logic? We're going to be doing some D flip-flops. Okay, so things are going to go in a certain sequence. So what we're going to take a look at is making something, well, sort of kind of like a counter, but not entirely a counter. But we're going to go like 0, 1, 2, 3, repeat. 0, 1, 2, 3, repeat. So we're going to do things in a specific order. So we're going to use that to drive some combination logic soon. So once we understand the basics of a D flip-flop, and we're going to get into flip-flops a little later on in the semester, but once we understand how a D flip-flop can drive a system, we can use that to make a stoplight as it goes through and kind of do a counter. We can add probably 3 or 4 of them to do that. Okay, so what really happens here, we've already talked about combination logic, right? Those are our AOI logic gates that we're going to use. We're going to use a certain set of inputs or switches and control a set of outputs. Now, what we do is when we're using sequential logic, we can take the flip-flops, which essentially store memory, and make our combination logic kind of just become automatic and routine in loop. Alright, so what I need you to make sure that you draw it down here is what the D flip-flop is. Okay. This is a good flip-flop, probably the easiest one I think you kind of work with and understand with everything that we're going to do in class. Alright, so on top we have the preset and the clear. Alright, so notice that there is a bubble with each one of those, which means it needs the opposite to preset or clear because they're inverted. Alright, we're going to send some sort of data in, okay, some sort of driven data that's going to go in. We're going to have a clock voltage. So if you remember back from signal analysis, a clock, right, it's on, then off, on, then off, on, then off. So it's just that square wave going in. And then we're going to have 2 outputs. We're going to have Q and Q bar. Obviously the opposites of each other. For this particular flip-flop, okay, it's going to change on the rising edge of the clock. And it'll make more sense when you see one that changes on the falling edge, and I'll show you how to do that. Okay, but let's go through what happens here. Alright, so if we look at this table here, we have preset, clear. If those are both a 1, and the clock's rising, and the data in is a 1, Q is a 1, and Q bar, or not Q, is a 0. Q and Q bar will always be opposites of each other, right? If we have preset and clear set to 1, and on the rising edge of the clock, our data coming in is a 0, Q will be a 0, Q bar will be a 1. In essence, we say that Q follows D. Q follows D with a flip-flop, okay, on the rising edge of the clock or the falling edge. But we're talking about it specifically here, a rising edge clock. Alright, so let's go with this other signal here. If preset and clear are both 1s coming in, and our clock is at a 0, right? Because our clock goes high, low, high, low, high, low. If our clock happens to be at a 0 there and the data in is a 1, okay, we're not going to change the output. It'll stay what it was. If we come in and preset is pressed, so preset and then clear is 1, okay, we don't care what the clock data is or what the data in is. The output will be a 1 automatically. Q will go to 1 when we hit preset. I know it seems backwards. When we hit preset, it makes the flip-flop go to 0 instead of 1. But it makes the output Q go to 1, Q bar 0, automatically, regardless of where the clock is in the data in. We're going to look at the signal analysis here, and that'll clear that up in a minute. Then, if we come along, and if preset's 1 and we hit the clear button, okay, and we hit clear, what happens? Q goes to 0, and Q bar goes to 1. And then we can't hit preset and clear at the same time. Illegal conditions, we can't have a 1-1. So it'll never get to that state when we have that, okay? So let's go through, talk about it a little bit, okay? There's multiple types of flip-flops. There's a JK flip-flop, there's a SR, there's, obviously the D1 SR is a set reset, JK is a different kind of toggle type of flip-flop that we'll talk about a little later on. But the D flip-flop essentially is a divide by 2. Every D flip-flop that we put in series with another one divides the previous one in half. Okay? So we're going to get into that in Unit 3 more in depth. But we're going to do this so that we understand the A to D converter board game, not really a board game, but the die roller that you soldered together. Okay? So let's go through this. So remember here, logic of 1 or true is what's in red, and logic of 0 is what's false right now. So we're going to start with the clock at 0. Alright, so the clock's going to pulse in at 0. Q is going to follow D. Notice how this is wired up, and this is why we feed Q bar into D, so that way it constantly changes. Alright, our preset and clear are both getting 5 volts. That's going to be important when you do everything in multi-sim later on to make these circuits. Alright, so this is our initial condition right here. Okay, and then what happens is, alright, the pulse in changes. Okay, the pulse in is going to change. We're going to have a rising edge of the clock here. Notice our preset and our clear haven't changed or done anything yet. So we're pulsing with the clock. Okay, so as this pulses in, okay, what's going to happen is we're going to change some values around here. So we pulsed in. Okay, we went high to low. So our pulse out, okay, is going to delay and then drop. Does this make sense as you're watching through everything? So on the rising edge of the clock, the pulse in, okay, our pulse out, our Q changed. It went from low to high. Okay, and then it sits on a cycle of the clock, and then the next time the clock has a rising edge, it only changes on the clock's rising edge. So what happened? The pulse in, we had a rising edge of the clock. I've kind of stopped it so you can kind of see like halfway through right here. There's a rising edge of the clock, a pulse in. That instantaneously changes our Q to 0 now. So Q will stay 1 unless preset or clear is hit. Okay, well obviously it'll stay 1 if preset is hit, but it could drop to 0 if clear is hit. But the point is, the pulse in, that's the clock, and our signal only changes on the rising edge of the clock here. So Q can only change when the clock edge rises, and it changes and it holds that position until the next rising edge. So it started out at 0, the clock pulsed in, we had a rising edge, Q went to 1. Okay, and it stayed at 1 until the next rising edge, and then it went to 0. So next, okay, what's going to happen is we're going to send in another clock pulse, another rising edge, okay, right there, and we got another rising edge of the clock. So when the clock hits the next rising edge, our Q goes back up to 1. Alright, so essentially it's a divide by 2. We're taking that clock signal, and it's a divide by 2 because the pulse out takes twice as long now. Does that make sense? If you're looking at the graph, alright, so now that, you know, if we're looking at periods, the period of the pulse out, okay, takes 2 periods of the pulse in. That's why it's a divide by 2 circuit as we go through and take a look at that signal. Okay, so remember, the pulse only changes, the pulse out only changes when the pulse in has a rising edge. Alright, so if we take a look, right, the third pulse is a repeat of the first. The fourth is going to be a repeat of the second. So over and over and over. Okay, and it's just going to sit here and loop and do this for us. Alright, so let's analyze this a little bit more. Okay, so if we're looking at the pulse out, so say we just did what we did over and over and over and over. So the pulse in, that's the clock, right? So the clock's going to go high, low, high, low, high, low, high, low, high, low, like it's doing. Notice the pulse out only changes every single time the clock has a rising edge. That's where the clock is going from 0 to 1. That's what I'm calling a rising edge. Going from 0 to 1, that's the rising edge. Okay? So we want to say and know the period of the pulse out is twice the period of the pulse in. Okay? So this is why it's a divide by 2 circuit. And this is really what we're talking about, okay? The pulse out, that's Q, and then the pulse in, that's the clock signal. Okay, so it's half the frequency. Okay, it's twice the period, but half the frequency when we do that. Okay, so let's take a look at what preset and clear does to the signal. If we go with that same signal, right, that changes on the rising edge of the clock. So every time the pulse in rises from 0 to 1, our signal should change. But what happens when we hit clear? When we hit the clear button, it automatically holds the signal to 0. Even if we let through the clear button, the output won't change again until the next rising edge of the clock. Okay, then, all right, as we hold the preset down, so if we hit preset, preset automatically sets the output to 1. Okay, and then if you let go of it in the middle of a clock signal, it won't change and drop back to 0 until the next rising edge of the clock. So it's very, very important that we understand how this signal works. Okay, so preset and clear. Preset automatically kicks it to 1. Clear kicks the signal, the output signal, to 0, or our cue signal to 0. Okay. Alright, so if we just want to review it, we have to understand we're going to do a 2-bit binary counter. Okay, a 2-bit binary counter. So 2 bits being 0 and 1, right, or 0 0 0 1 1 0 1 1. So those are the 2 bits because there's only 2 digits involved. If it was 3 bits, it would be like 0 0 0 all the way up to 1 1 1. Okay, 4 bits would be 0 0 0 0 up to 1 1 1 1. Okay, so when we do this, all right, 0 0 is 1, 0 1 is 2, 1 0, I'm sorry, we start at 0. 0 0 is 0, 0 1 is 1, 1 0 is 2, and 1 1 is 3. So that's how we're going to count. Okay, so when we want to do, okay, a 2-bit counter here, we need at least 2 flip-flops. Okay, 2 flip-flops, because the first one is only going to go 0 1 0 1. It's only going to count from 0 1. So we need to add another flip-flop in it. We place that flip-flop in series. Please note how these guys are wired. Okay, the preset and clear for both flip-flops both go to 5 volts. We send our square wave clock signal in, that's 5 volts. Alright, and then we have an output A and an output B. Those are the cues from the flip-flops, and then we feed the not cues, okay, back into D. And how do I know they're not cues? Well, there's a little bubble there. Remember, that's the not sign. And then there's a tilde next to the 1 cue and a tilde next to the 2 cue. So that means that they're the not cues. Okay? So we got to take a look at what happens in the signal here. Okay, the little blue arrows here on the signal represent the rising edge of the clock and what happens to the signal. Okay? So the output B, okay, comes from the first flip-flop. So notice that that took the clock signal and divided it in 2. Output A comes from B, okay, B is the clock signal for A. Okay, so we'll read these backwards. The flip-flop on the left is B, and the flip-flop on the right is A. This is going to become important because we're going to talk about least significant bit and most significant bit very soon. Okay, so the most significant bit would be the leftmost bit, the least significant bit would be the rightmost bit. Okay, and that's why we have to start thinking about things in that term. And we're going to cover this soon. Okay, but notice that A, since it's coming out of the second flip-flop, okay, it's twice as long as B. Okay, so that's really what we're talking about here. Okay, so what does that mean when we analyze the signal? When A and B are both 0, our output should be a 0, which means our little probes out there, A and B, should not be turned on. Okay, so we're basing it on our clock signal. Alright, then the next signal, what happens? We end up with 0 1. 0 1 is triggered on the rising edge of the clock. So the little blue arrow, Okay, on the clock end, that's the rising edge of the clock, and that's what triggers this count. A 0 for A, a 1 for B. 0, 1 is equivalent to the number 1. So that's binary to decimal. Okay? Then we're going to have another trigger on the next rising edge of the clock. On the next rising edge of the clock, where the little blue arrow is, A will go to 1, B will go to 0. So we will have 1, 0 now. 1, 0 in binary is the number 2 for us in decimal. Then, on the next rising edge of the clock, A will go to 1 and B will go to 1. A was already at 1, right? But B is going to be at 1. So we have a 1, 1. So 1, 1 in binary is equivalent to the number of 3 in decimal for us. So we have just gone 0, 1, 2, 3. Look at what's next. Okay, next rising edge of the clock, what happens? A and B both drop to 0, and we start all over. Okay, it is important that this is how it's wired up though. Okay, the Q naughts feed the D's. Okay, so that part is important. You guys will build this in multisim and make this work, and we will breadboard this so that you understand how to make this count 0, 1, 2, 3, 0, 1, 2, 3. Also, when we count with digital, we always start at 0. Okay, well, I mean, I'm going to make you do other different kinds of counts, but essentially that always counts as our first digit. Okay, so even though this is a 2-bit counter, right, we have 2 bits, we have bit A and bit B. Alright, so it's a 2-bit counter. The most that we can count to in a 2-bit counter is 4 digits, those digits being 0, 1, 2, and 3. Alright, so here's what it looks like on the IC chip. Okay, and it's a 74 chip. Okay, so it's a 74 LS74N. So the 74 chip is a D flip-flop, and you have to make sure that you pay attention to what's getting wired into what pin when we do our breadboarding here. So we will have the data sheets to look at when we go through this, and we're going to do a section on data sheets so that we understand. But essentially we can fit 2 flip-flops on one chip. All the chips we're going to use are 14-pin chips except for the 555 timer. Okay, he's only an 8-pin chip. But so when we do this, alright, you have different pin numbers, alright, and you have to make sure that the right pin number when you wire this up. So pin 1 and pin 4, those both go to 5 volts. So when you breadboard that, you got to make sure that pin 1 and 4 go to 5 volts. Okay, you have to make sure that Q bar goes to D. So pin 6 has to connect to pin 2. Alright, pin 3 has to get the clock input. Alright, and pin 5 is going to go to like an output LED for us. Okay, the clock that we're going to use to breadboard is the clock that's on your breadboard companion. Alright, that you've soldered, the little blinking green light. Right, that's our clock signal, and we can use a variable resistor to change how fast it toggles through that. Right, you spun that and saw that the light went fast, the light went slow. Alright, and then the other flip-flop, okay, is on the other side of the IC chip, and it's important to know what pin goes to what. So when you guys print out like the schematics and everything, I would always try to print your wiring diagrams so you know where your wires go. Alright, those tell you exactly what pins to put those wires to, and it makes it a lot easier when you're studying your schematic and you have to breadboard all this, because breadboard's going to get a little tricky later on. But if we do enough in the beginning and get good at it, alright, we won't have as many issues later on when we start getting into these. Because, you know, once we get into these and have to troubleshoot them, then it becomes a little bit of work as well. Okay? So, that's sequential logic for us. We're going to build this in multisim and make it work. We're also going to do a hands-on lab where we're going to breadboard this and make it work. It's very important that we can do it, you know, simulate it on the computer and physically make it work by hand. Alright? We'll see you guys in class.